This is another chemical reaction problem where we have 2H2 plus 1O2 is combusted into H2O. So this is a combustion reaction of hydrogen and oxygen forming water. And for this chemical reaction, the change in the concentration, which is the reaction rate, the change in concentration of H2 is proportional to the square of the concentration of H2. So this is a fairly typical chemistry problem. And those of you who know something about chemistry would know that, or might recognize that the the proportional to the square of concentration is to do with this coefficient here. Now you don't need to know this because we've actually got it in the equation, but that coefficient of 2 affects the reaction rate by the square of that concentration. Okay, so we've been given the differential equation though. So we're going to start with this differential equation. Okay, the rate of change of concentration, or the reaction rate, is proportional to the square of the hydrogen concentration, or H2 concentration. And we're going to then solve this differential equation. So this differential equation, I'm going to write as d, and this is our dependent variable y. We're just going to leave it as H2 this time, over dt is equal to some constant value times the concentration of hydrogen squared. So we're going to separate these variables. So we get the change in the hydrogen ion concentration, or sorry, the hydrogen gas concentration over the concentration squared is going to be equal to some constant times dt. So we've now separated our y variables to the left, our t variables or x variables to the right. We have separated our variables. We are going to then integrate both sides of that equation. Integrating this, the left side, we're going to use power rule. So we're going to end up with -1. The power is going to end up being -1. So we get -1 over H2 to the power 1. And that's going to be equal to, and again, I've used a power rule here. Be careful not to use log. On the right-hand side, it's going to be equal to K times T, and then we're going to have this plus C to solve for. So in this case here, we're not given an initial condition, so we're going to have to solve this algebraically, and we're going to solve it for the dependent variable, the hydrogen gas concentration. So we're going to rearrange this equation, and I'm going to basically cross multiply this. So I get -1 over KT plus C, and that's going to be equal to my dependent variable H2, and then this is going to be my function. So my H2 concentration as a function of time is equal to -1 over K times T plus C. So these problems are our differential equations. Typical differential equation problems involve growth and decay, so exponential growth and decay. So a population growth proportional to its size is governed by the differential equation dp, or the change in population over the change in time, is equal to some constant rate times the actual population. So again, we should expect this to end up as an exponential equation. And this particular population, it says it's growing at 5% per year. That K actually represents the continuous growth rate. So if it grows at 5% per year, that 0.05, that multiplier represents 5% as a continuous growth factor. So we're going to set up this equation. So we end up with the change in population, dp over the change in time, dt, is equal to some constant 0.05 times p. And we're going to separate these variables. dp over p is going to be equal to 0.05 times dt. Okay, separating the variables, we then integrate. And this becomes an exponential problem because when we integrate this, we're going to get log of p, and we're going to have to undo that log with an exponent. So that's going to be 0.05 times our t value plus c. So rearranging this to solve for p, we're going to end up with p as a function of time is equal to e to the power 0.05 t plus c. And again, that plus c, it's good to recognize that that plus c is going to end up as some k value on our exponential function. So we end up with pt is equal to, and I'm going to rearrange this to e to the c times e to the 0.05 t. Again, you don't necessarily need to go through this step if you know that that e to the c just represents the starting value, or k. Okay. So we're going to put our initial condition in. Okay, our initial population starts at 1,000. That means at t equals 0, our population is equal to 1,000. We can plug that in, so we're going to end up with 1,000 is equal to, we're solving for k, and we know that our t value is equal to 0, so 0.05 times 0, that becomes an exponent of 0, and that solves for k. K then works out to be 1,000. So again, if you know what this equation is going to look like to start with, you know that at this point we've solved this problem. So that expression, that constant in the front, should represent the initial population, e to the 0.05 t. There's our equation, and that 0.05 represents 5% continuous growth rate.